Hello, good morning to everybody. Expecting that all of you are doing very well, and a warm welcome to a new academic year. In our subject, we just start the pending or maybe the remaining portion of the second semester topic in first time. After that, we will pass on to the third semester topic. So, in the second semester, the course is probability theory, and the first module deals with the introduction to probability. I just summarize the different area which are already we covered one. So, in the introduction to probability theory part, we addressed a different approach or definition of probability, such as classical definition, statistical definition, as well as axiomatic definition, and subjective probability. We just pass through it. Initially, we defined different aspects or terms of this probability, such as random experiment, sample space, mutually exclusive, and so on. Just look at one by one. The one approach to or one type of definition is the classical definition or mathematical interpretation of probability. If the random experiment produces only a finite number of outcomes and all the outcomes are equally likely, and let f be the number of outcomes out of n which are favorable to a particular event A, then the probability of the event to happen is given by P of A is equal to f by n. Using this one, we can do so many different type of problems. And another approach is statistical definition. It is a empirical definition also. The random experiment is repeated n times under the same initial conditions. If the event E occurs f times, then the ratio f by n is called the relative frequency, and the probability of P of E is given by P of A is equal to limit n tends to infinity f by n. You will study the more features of this one in law of large numbers. And the most popular one is axiomatic definition. Consider a random experiment with a sample space S, and let P is a function defined from the set of all events script B of the random experiment, where B is a set of Borel set. Then P is a probability measure if it is satisfying the following axioms. First one, for any event E in script B, P of E is greater than 0, or we generally called as non-negativity condition. Second one, P of S is equal to 1, where S is the sample space, that is a certainty condition. Third one, for any sequence of mutually exclusive events E1, E2, extra, probability of E1 union, E2 union, E3 union, extra is equal to P of E1 plus P of E2 plus P of E3 extra. That is, probability of union EI is equal to summation over I P of EI, and we called it as additivity condition. If these three axioms are satisfying, then P is a probability measure. And another one is subjective probability. This interpretation of probability deals with the degree of certainty or belief about the occurrence of an event. Most often this probability associated not so much with an event as with the truth of a proposition asserting the occurrence of this event. In some situation, the value of a probability of an event may sometime be assessed by one's own judgment or belief. So we can't clear cut definition does not provide for subjective probability, but for a layman concept it may be used. For example, what is the probability that tomorrow is a rainy day, or that is, what is the probability that 2021 January 1st will begin a world war, such as that one. So some expert opinion or maybe one's judgment or belief will provide a probability one. That these all are covered in the previous one, and also using this subjective axiomatic definition, we already covered addition theorem and so many preliminary aspects of probabilities. Now we pass on to conditional probability. Suppose we are rolling a die, and let us denote A, B, C and D are the 4 events, where A is the event which represents the phase number is even. So in the sample space S is equal to, that is a set 1, 2, 3, 4, 5 and 6. So A, the phase number is even, which means that A is equal to set 2, 4 and 6. We consider B as the phase number is less than 5, that is B is equal to set 1, 2, 3 and 4. C, the phase number is a prime number, so C is equal to set 2, 3, 5, and D, the phase number is a multiple of 3, that is D is equal to set 3, 6. Now if the outcome of the experiment is 2, we conclude that A has happened, B has happened, C has happened and D does not happen. So one realization may relate so many probable events. So the occurrence of a single outcome can imply the simultaneous occurrence of several events. In some situation, we have no idea about the actual outcome produced by the experimenter, even though we have the list of possible outcomes with us. That is, we are considering unconditional probability. But in conditional probability, there are two pieces of information. A, the experimenter has performed the experiment, and B, an observer at the experiment has informed us that event B has happened. Against the new information B, the probability of P of A, P of B, P of C and P of D extra are likely changed. Instead of old probability P of A, which is simply, that is 3 divided by 6 in the previous case, the more relevant probability is P of A given B, which stands for the probability for the happening of A given that B has already happened. The new probability P of A given B is called the conditional probability of A given B. So if an additional information, that is B, the event B is happened, that we know. So sometime it may affect the happening of A, sometime no. So if so, what is the new probability, that is P of A given B? If B is already happened, what is the chance of occurring A? So in conditional probability, we are actually updating the old probabilities according to the new information B. With the information of B, B becomes the sure event or the new sample space for the determination of probabilities of various events. If you are considering P of A, actually it is P of A given yes. That is, the sample space will be the sure event. In this case, we conduct, that is, reduce our sample space into B, which is favorable to us. Passing on to the definition, that is, let A and B are any two events in the event space script B associated with the probability space script SBP. The conditional probability of event A given B is defined as P of A given B is equal to P of A intersection B divided by P of B if P of B greater than 0, and is left undefined if P of B is equal to 0. If P of B is greater than 0, then only this conditional probability will exist, or that is valid one. In the same manner, if the A is already occurred, then the conditional probability that event B given A is defined as P of B given A, which is equal to P of AB divided by P of A if P of A greater than 0, and is left undefined if P of A is equal to 0. So this is the definition of conditional probability. Now we just pass on some illustration. A fair coin is tossed twice and an observer reports that at least one toss has produced a head. Given this partial information, determine the probability that both tosses have produced heads. So we have to define the event A as well as B. Let A defined as both are heads. So the probable outcome is that is set HH, and B represents at least one is H, that is our new information. So it is set HT, TH, HH, and the intersection of A and B is only singleton set, that is set HH. So P of A is equal to 1 by 4. By using the classical definition of probability, P of B is equal to 3 by 4 and P of AB is equal to 1 by 4. Now P of A given B is equal to P of A intersection B divided by P of B, which is equal to 1 by 4 divided by 3 by 4, so which is equal to 1 by 3. So the probability is little higher or maybe more certain one. We pass on to another one. A die is rolled twice and it is informed that the two phase numbers are different. Based on this information, determine the probability for the sum is 7, 4, 12. In earlier case, this additional information, that is two phase numbers are different, that information is not known. So we have to eliminate from the sample space as 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6. So we just look at its a solution, that is we defined 4 type of events. A, which represents the two phase numbers are different, B is equal to the sum is 7, C is equal to the sum is 4, and D is equal to the sum is 12. So in this particular problem, if a die is rolled twice, the sample space naturally contains 36 events, out of which 6 outcomes are phase numbers are same. So that is A represents the two phase numbers are different, then the set A contains 30 elements. So P of A is equal to 30 divided by 36, and P of B is equal to 6 by 36. So since B contains 6 elements, that is the sum is 7. So it is 1, 6, then 2, 5, 3, 4, 4, 3, then 5, 2, and that is 6, 1. Similarly, P of C is equal to 3 by 36 and P of D is equal to 1 by 36. And we consider their intersection part, that is AB contains at 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, and AC 1, 3, 3, 1, and AD which is equal to 5, because we have an information that the two phase numbers are different and the sum is 12, which is an impossible event, so AD is equal to 5. And correspondingly, the P of AB is equal to 6 by 36, P of AC is equal to 2 by 36, and P of AD is equal to 0. So probability of B given A is equal to P of AB divided by P of A is equal to 1 by 5, P of C given A, C is equal to P of AC divided by P of A is equal to 1 by 15, and P of D given A, which is equal to P of D intersection A divided by P of A, which is equal to 0, which is the solution of the given problem. So using this conditional probability, that is we are conditioning, we have some other that is constraint or maybe information, we can improve our probability. That is that the case are considering the conditional probability. You just see the video which are given below, so you can obtain a more good clear idea about this conditional probability. So thanks.